Good morning, class. Here we are, the last week of instruction. And I graded your exams over the weekend from last week, and I've graded a couple more of your labs, but I still got a bunch more to go. So I haven't posted those grades on WebAssign yet to integrate with the rest of your grades from the semester. And I have yet to post the solutions to Exam 3, but I will be posting them, and I will be moving your grades from Sakai over to WebAssign sometime soon. But if you're interested to see how you did, you can go to Sakai, and the results should have been released this morning, and you should be able to read my feedback and my comments. Okay? So, another exam in the books. Next up, final exam. All right? So that's what's on the well, this week, the agenda for this week is we're going to learn more about rotational mechanics. All right, so here is the situation for today. I'm going to organize. This light is really bright. I'm going to organize our thoughts today by posing this question. Okay, so you have an incline and a hill. You have a hill, and you have a hoop, like a hula hoop, and you have a disc. What's the difference? A disc is solid, a hoop is not, but they have the same mass and the same radius, so they're the same size. Same size. And you line them up on the top of this hill, and you let them go from rest, and they start rolling down the hill, gaining speed as they go, as they roll down the hill, as the stored up gravitational potential energy becomes kinetic energy. And the question is, which of these objects, the hoop, which is open in the middle, or the disc, which is not, gets to the bottom first? Another way of answering that question is, which one's traveling faster when he gets to the bottom of the hill? All right, so your first thought might be, well, won't they get to the bottom of the hill at the same time? You know, two things, same mass, same radius, rolling down a hill. They start with the same amount of energy, won't they end with the same amount of energy? And to that question, I'd say yes. Yes, let's assume mechanical energy is conserved. So these objects start with some potential energy, and that becomes kinetic energy as it rolls down the hill. But saying that they have the same amount of energy is not the same thing as saying they're traveling at the same speed, because now we have a new kind of energy to think about. That's rotational kinetic energy. Okay? So let me set this problem up on the dry erase, well, my tablet whiteboard, and we will take it from there. All right, you got questions while I'm working? Put them in the comments, and I'll see them as we're doing this. All right. Hope you guys had a great weekend. I took a great walk in the woods. Seeing it was pretty windy and a little chilly, but it wasn't so bad. The days are getting shorter, the nights are getting colder. Trying to enjoy what's left of the season. All right. So here is. Excuse me. So here's the situation. I'll draw them side by side here. So we got these two hills, and here's the hoop. All right, and wow, that's a really bad hoop. So it's hollow in the middle and thin, but it's open in the middle. And then right next to it on another hill is the disc. Okay, which is the same size, but it's completely filled in. All right, so these two things, these two objects have the same mass, let's call it m, and they also have the same radius, call that r. Oops, I took a bite out of my hoop. Okay, so they're the same size, but they're not the same. One's hollow in the middle. And they start at the same height. Okay, their initial y position is h relative to the ground. Okay, now as these things start rolling, they're going to start picking up speed. All right, they start from rest, but they're going to start picking up speed as they roll down the hill. And we can think about these two moments in time as 1 and 2 for each of these objects. The starting position is at the top of the hill, call that position 1. The ending position is the bottom of the hill, call that position 2. So we're going to assume that mechanical energy is conserved. There's no non-conservative forces like friction or air drag acting on these systems. And we're going to set up an energy balance equation. So the energy these objects start with is equal to the energy they end with at the bottom of the hill. All right, and we'll take a look. Actually, this equation is going to look the same for both of these. At the top of the hill, well, what I'm saying is we're going to set up an energy balance equation where the energy at the top of the hill equals the energy at the bottom of the hill. All right, well, at the top of the hill, all the energy is potential energy. It's gravitational potential energy, which is equal to the weight. Both of these objects have the same weight because they have the same mass, times height. Gravitational potential energy is weight mg times height. At the bottom of the hill, all that potential energy has become kinetic. 1/2 mv squared. But there's another kind of kinetic. All right, the kinetic energy is now, part of it is the term I just wrote out, the 1/2 mv squared, is translational kinetic energy. But these things are also going to rotate as they go down the hill, which means they're going to pick up rotational kinetic energy, which isn't 1/2 mv squared, it's 1/2 I omega squared, where omega is the angular velocity of the wheels, how quickly they're rotating. And from last week, there's a connection between this linear speed and this angular speed. And it's, well, I'll use the same symbol here. It's the radius. So the linear speed, v, is equal to the radius of the wheels times omega, how fast they're rotating in radians per second. So a point, and so in this case, what I'm arguing here is that the speed with which these wheels travel through space is the same speed that a point on the edge of the wheel is rotating, is traveling tangentially relative to the center of the wheel, the axis of rotation. And this is true because there's always a point of the outer edge of the wheel that's in contact with the surface of this incline. So the speed with which the center of mass is rolling down the hill linearly is equal to the speed with which a point on the side of the wheel is moving tangentially to the wheel as it spins around, because this point is in contact. All right, so we can connect. Well, why don't we do that right now? So we can get rid of the omega in this formula, because if v equals r over omega, or r times omega, v divided by r equals omega. So we could plug that in down here to get rid of omega. Okay, so what's this energy equation is the same for both of these wheels, the hoop, the one that's open in the middle, hollow in the middle, and the disc. But there's a term in this this formula that is not the same for the two objects. Which term is not the same for the two objects? There's only one here that could possibly not be the same. One constant in here that would not be the same. Anybody have any ideas? I think you guys did pretty well on the exam, by the way, overall. Pretty good job. Inertia. Thank you, Katie. That's right. The rotational inertia, the I, right there, The I is going to be different for these two objects. And let's do some integrals now to calculate what the I is, the rotational inertia is for these two objects. And then we'll come back to this problem. So I'm going to come way over here. I'm going to try to. There we go. Okay. And let's start with, well, let's start with the hoop. All right, and this will make the disk easier too if we start with the hoop. So we start to set up, you know, what does a hoop look like? What's the geometry of a hoop? Well, let's assume that it's you have to excuse my wavy drawing. It's hard to draw circles freehand. So the axis of rotation is in the middle, and a hoop has a radius, and let's assume that this hoop is very, very skinny. Okay, so we could call well, let's not do dr. Let's say that it's very, very skinny, so it doesn't really have much thickness. Okay, it's a very skinny hoop, and there's a little tiny chunk of the hoop here that has an infinitesimally small mass. Okay, so one thing you could do is, well, let's write out the formula for finding rotational inertia. And the general form is you integrate all these infinitesimally small pieces of mass after multiplying by their position, r squared, relative to the axis of rotation. Their position squared relative to the axis of rotation. Okay, so here a hoop is a circle. So one way you could integrate over all these little tiny pieces of mass as you go around is to just integrate around the circle. I'm going the wrong way, I guess. So the limits of integration here could be 0 to 2 pi. 2 pi radians. That would be going around in the circle. Okay? Integrating around all these little pieces of mass. So one thing we have here is, well, the dm is the limits of integration are units of angle, and dm is units of mass. So we have this disconnect between what we're integrating with respect to and our limits of integration. So we got to do a change of variables here, and the way to do this is to recognize that there's a connection between a little tiny angular displacement, d theta, zoom in here a little bit, and a little tiny arc length, ds. Okay, so the connection here is this little tiny arc length right here is equal to this little tiny angle d theta times r. So we have r d theta equals ds. Okay, and another thing we got here is you know, this is a long skinny hoop, and you could imagine unrolling it like this, in which case its length would be the circumference of the hoop, and these little dm's are little chunks of this thing. And remember we talked about, you know, you have a long skinny rod, you can define the density, the linear density of this object as the total mass divided by the total length, which in this case would be the circumference of the hoop. Okay, so that will come in handy. All right? So then the only last thing we need to connect this all together is a connection between ds and dm. And so ds is, in this picture here, ds is this little tiny length of the entire hoop when it's spread out. And we know that if we take that little tiny length and multiply by this linear density, we'll get the mass of that little tiny chunk, dm. So dm equals ds lambda. So let's put all this together into our integral and see if we have succeeded in matching our limits of integration with the thing we're integrating with respect to. All right, so we'll have the integral from 0 to 2 pi. And now r is a constant. Every little piece of this mass is the same distance away. Capital R squared, that's a constant. And dm is lambda ds, lambda times ds, and ds is r d theta. So the lambda is a constant. Let's go down here. The lambda is a constant, so we can pull that out of the integral. And we have the integral from 0 to 2 pi. Well, the r is a constant too, sorry, so we can pull that out. So we have an r squared times r cubed. In this case of the hoop, the r is a constant. Every little piece of the hoop is the same distance from the axis of rotation. So we're just integrating with respect to theta. So we have the integral from 0 to 2 pi of d theta. And that's going to equal just theta evaluated at 0 and 2 pi. And that's going to equal, well, theta evaluated at 2 pi gives us 2 pi. Theta evaluated at 0 gives us 0. Okay, so we have rotational inertia equals 2 pi lambda times r cubed. Well, lambda is m over 2 pi r. So this simplifies to mr squared. And this is our solution for the rotational inertia of a hoop. It's its mass times its radius squared. The rotational inertia of a hoop. So all right, so let's not go back to the original question yet. Let's move on and think about the rotational inertia of the disk. Right, the disk. Right. So our result that we just got is going to be easier, is going to make this one easier because, here we go, a disk is just a bunch of hoops. All right, and let's see. So the disk has a radius, but each hoop is at some intermediate value, call it little r. So big R is a constant, but little r is going to change from 0, the center, to big R, the exterior. As you know, so this, the disk is a bunch of hoops, okay, and we're gonna integrate over each of those hoops, and each of those hoops is going to have a rotational inertia that is given by the result that we just got, the mr squared, except in this case it'll be dm, a little tiny piece of mass, and we're integrating from the middle to the edge. All right, so that means our integral is going to be the integral. It will always start with the same form. It's the integral over all these little tiny pieces of mass, dm, but here we're going to integrate from the center of the circle to the outer edge, the center of the disk to the outer edge. So from 0 to big R. All right, and so let's think about, so actually in this case, this little hoop is like infinitely thin. Okay, so this little tiny hoop has an area associated with it, and we can call, and it has a mass associated, we'll call that dm. Okay, so the dm in our integral is the mass of this hoop, this infinitely thin hoop. All right, so in this case, here, let me draw the hoop out again. So if I splay this hoop out, you know, cut it and unravel it, the length of that hoop would now be 2 pi little r, and the thickness of that hoop is going to be a little tiny, well, let's use, so a little tiny distance moving from the center to the edge is a dr, little tiny distance. So the thickness of this hoop is dr. Okay, so what's the area of this hoop? The area is going to be the circumference times the thickness, 2 pi r dr. Okay, so let's define a new kind of density, and we'll call, let's say that this is rho. Okay, rho is a mass per unit area. So not a linear density, not a volume density, but an area density. Okay, and so we could write out that for this disk, the total mass divided by the total area of the whole disk would be its area density. And the area of a disk is pi times its radius, which is big R squared. Okay, and so if we take the area of this little tiny piece of hoop, 2 pi r dr, and multiply by this area density, we'll get a dm. I guess what I should have said is you can think of this as a little tiny area, dA. So the mass of that little tiny area dA is going to be the density of this disk times that area, which is going to be rho 2 pi r dr. Okay, so now we have our expression that allows us to do this change of variables up here, and then we can do the integral, because we're going to integrate with respect to r, and our limits of integration go from 0 to big R. Okay, so let me zoom out a little bit, and so you know, we're doing these integrals here at the end of the semester. I want you guys, you're going to have to be better at integrals next semester, at least in the second half of the semester. All right, so you got to you got to you know, it's good to get a little bit of work in here at the end of this semester. All right, so we're going to integrate from 0 to r squared, and now dm is the area density times the circumference of the little hoop, 2 pi r, times its thickness, dr. And so if I look at this expression, the rho and the 2 pi are constants, so we can pull that out. So we get rho 2 pi, and then we're integrating from 0 to r, and then r squared times r, it's r cubed dr. Okay, so that's going to be rho 2 pi. The integral of r cubed is increase the exponent by 1 and then divide by the new exponent. And then we're going to evaluate at r and subtract off whether that quantity is evaluated at 0. Well, 1 over 4 r to the 4th evaluated at 0 is 0. So this is going to become 1/4 big R cubed, or big R to the 4th, minus 0. Okay, and the rho again is m over pi r squared, so let's put that in there. We have m, so the rho is m over pi r squared, the mass of the disk divided by its area, multiplied by 2 pi, and then we're going to multiply by the 1/4 r to the 4th. Okay, so we'll have, let's see, what's going to cancel here? The pi's will cancel. We have a 2 up high and a 4 down low, so that'll become a 2. Got an r squared and an r to the 4th, so that'll become a 2. So you put this all together, and you get 1/2 mr squared. All right, so now we have our result for the disk. If I zoom out here a little bit, nope, can't zoom out. Well, I can do this. You see the result for both of these. So we have the rotational inertia of a disk that's the same mass and radius as a hoop is exactly half as much, 1/2 mr squared versus mr squared. So the disk has less rotational inertia, which means it should start spinning more easily, more readily. So we already have our answer. The disk is going to win this race to the bottom of the hill because it takes less energy to get it to rotate. There's less resistance to rotation. All right. Another way to think about this is the reason the hoop has more rotational inertia is it has the same amount of mass as the disk, but that mass is further away from the axis of rotation. And the disk having more mass closer to the axis of rotation makes it easier to rotate. All right, so but let's actually go to the end here, and now that we have our expressions for rotational inertia, we'll come back here, and let's do the hoop first. Okay, so with the hoop, this formula becomes mgh equals 1/2 mv squared plus 1/2, and now I, the rotational inertia, is mr squared, and omega is from up here, v divided by r squared. Okay, so all these terms have big M in them, so that'll cancel and go away. And then we're going to get GH equals 1/2 V squared plus, let's see, we'll have a R squared over R squared, so the R will cancel in that second term. We get a 1/2 V squared. So we get two 1/2 V squareds, which is just a V squared. So V, the speed of this hoop at the bottom of the hill, is going to be the square root of G times H. Okay. So there's the result for the hoop. Now let's take a look at the disk. I think I can do it down here. So mgh, the gravitational potential energy at the top of the hill, is equal to the translational kinetic energy at the bottom hill times the rotational kinetic energy, where now I, the rotational inertia, is not mr squared, but 1/2 mr squared. Times the angular velocity, or angular speed, which is linear speed v divided by r squared. So again, every term has an m in it, so that'll cancel. We'll get, over here, this r squared will cancel with that r squared, and this will become a v squared. And then, so we got, we simplify this, we're going to get gh equals 1/2 v squared plus 1/2 times 1/2 is 1/4 v squared, which is 1/2 plus 1/4 is 3/4 v squared. Now I'm going to write the final solution over here. So if I solve for v, I'd get v equals 3/4 is 4/3 gh square root. So here's our result for the hoop. So which of these quantities is smaller? So these quantities represent the speed of the hoop and the disc at the bottom of the hill, and 4/3 is bigger than the square root of 4/3 GH is bigger than the square root of GH. Not by much, but it is bigger. Okay, so the disk gets to the bottom of the hill first. Is that what I said earlier? I think that's what I said earlier. The disk gets to the bottom of the hill first because it has less rotational inertia. If I didn't say that earlier, that's what I meant to say. The hoop takes longer because it has more rotational inertia. So you could repeat this with, let me ask you, so here's a concept question, all right? In this case, you have a disc and a hoop, and this exact result would extend to a cylinder or a hollow cylinder, because all a cylinder is a bunch of discs, and it has the same rotational inertia about its axis through the middle. But what about, all right, let me ask you a concept question. Here the disc has less rotational inertia than the hoop because they have the same mass and the same radius, but the disc has more mass near the center, the axis of rotation. The hoop, more mass is further from the axis of rotation, and that means it has larger resistance to changes in its rotation, more rotational inertia. So what do you think, which of these, let's say you have two spheres, all right, two spheres, like bowling balls, all right, and they have the same radius and the same mass, but one is a solid sphere made out of, I don't know, let's say wood, and the other one is a hollow sphere made out of lead, okay? So they have the same total mass, but one's solid and the other's hollow in the middle, and they have the same radius. Which of those spheres, the hollow one or the solid one, would have more rotational inertia? Which of those spheres would have more rotational inertia? The one that's solid or the one that's hollow? They both have the same radius and they both have the same total mass. What do you say? Looks so sunny outside today. While you're thinking about this, there's an interesting result. If you do this this same calculation we did, but with solid spheres of different radius, do you think that the radius impacts which sphere gets to the bottom first? That's an interesting problem. Solid sphere versus hollow sphere. Which has more rotational inertia? They have the same mass and they have the same radius, but one is made out of dense metal and is hollow in the middle, and the other is made out of less dense wood and is solid in the middle. So I can't remember, what was my question? Which one has more? I can't remember if I asked you what has more rotational inertia or less rotational inertia. So William responded solid. Is that the solid has more or less, William? Is this this isn't working. Hollow is more, solid is less. Okay, so Thomas says hollow is more, solid is less, and that's exactly right. All right, so Thomas Thomas has it. The solid is going to have less rotational inertia because more of its mass is located near the center. And the hollow will have more because its mass is further away from the axis of rotation. So if you raced these two spheres down the incline, the hollow one would lose. The solid one would win. This just reminded me of a little experiment. This doesn't have anything to do with rotational inertia, but it has to do with the physics of how things rotate. You should do this experiment. If you have two eggs, and one is hard-boiled and the other one is raw, take those, and they're the same size, roughly the same size, and put those eggs on the tabletop and spin them. Okay, and then observe what happens. It's really cool. The thing that you observe is not due to the rotational inertia, but the fact that when you spin a raw egg, the liquid inside doesn't spin in the same way the shell does, and so you have this viscous fluid in there which saps up energy. You should try it sometime. It's really neat. So take a hard-boiled egg and a raw egg, roughly the same size, and spin them and see which one spins better. And it becomes a way that you can tell whether an egg is hard-boiled or not by the way that it responds. Okay, so let's see. I think let me end today by defining a new concept for you. We already talked about this, torque. But let's take a little bit closer look at what torque is, and then call it a day. All right. So back to my whiteboard. Oh, by the way, I might on the final exam I might ask you to calculate the rotational inertia of an object like a long uniform rod or a hoop. Or a disc, but I won't ask you to calculate it unless we did it together. All right. What I'm saying is I might ask you to do an integral on the final exam, but I wouldn't make you do it not having seen it before. So we haven't done a sphere. I wouldn't say find the rotational inertia of a sphere. The way to do that is to first find the rotational inertia of a shell, a hollow shell, and then a sphere is just a bunch of hollow shells. But I won't ask you. Let's say I give you a problem that says find the rotational inertia of a fan that has 5 blades, and each of those blades can be approximated as a long uniform rod, like we looked at last time. So the total rotational inertia is just 5 times, because there's 5 blades, 5 times the rotational inertia of each of those blades. But I won't ask you to figure out that the rotational inertia of a long uniform rod is, 1/3 times its length times r squared. I will give you the formulas that you need to find rotational inertia in the problems that I give you on the final. The only exception is if that's the point of the problem, to find the rotational inertia of an object. Then I won't give it to you. You'll have to calculate what it is using the definition of the integral definition of rotational inertia. All right. Now back to this. So torque. Let's say there's a door. All right. So we're looking down from above. Here's the hinge. Okay, the hinge is the axis of rotation, and the door, looking down from above, looks like an arm, like that. And then you exert a force on the end of the door, and there's 2 factors that determine how effective you are at moving that door, shutting it or opening it. And the one factor is where the force is applied. Like if I apply that same force in here, closer to the axis of rotation, it's not going to be as effective. You want to try this. You should try this sometime. Just go to a door and try to close that door by pushing on the door close to the hinges, it's a lot harder. But so the door handle is far away from the hinges, and that makes it easier to move. So where the door is rotated by an exerted torque, but where you apply the force relative to the axis of rotation influences how strong that torque is. Okay, so that's one factor, where the force is applied. Another factor is the angle with which the force is applied. And so maybe you can call the distance from the axis of rotation to where the force is applied r. Okay, but the force may make an angle with, so you can imagine one vector points along the door, call that r, from the axis of rotation to where the point to the point where the force is applied. And another vector, the force, can have a direction theta relative to r. Okay, so the way you calculate, when we talked about torque last week, I said, well, torque is RF, but really this doesn't take into account. This takes into account the positional nature, the fact that R matters, how far away from the axis of rotation matters, but it doesn't take this angle factor into account. So a better way to write out torque, which becomes a vector, is R cross F. So what the heck is this? This is called a cross product. Okay, remember the dot product between two vectors? Well, the cross product, one way to calculate the cross product is RF times the sine of the angle between those two vectors, R and F. There's another way to calculate the cross product, but maybe we have to take a look at the homework. I'm not sure it's we're going to do that this semester. I don't know, let me think about it. It involves, so this is a matrix, or no, sorry, it's a vector calculation, and it's called another name for the dot product is the scalar product, because the result is a scalar quantity. Well, the cross product is also called the vector product because the result is a vector. And so the way to think about this is the reason it needs to be a vector is because a torque, if you have a door, a torque exerted on that door can result in two flavors of rotation. It can cause the door, looking down from above, you can cause the door to rotate clockwise, or it can cause the door to rotate counterclockwise. And so that's two different flavors of rotation. And you got to take that into account. So the way to determine, so here in the example that I'm drawing, the torque is directed, it's a vector quantity, and it's directed out of the screen toward me. All right, that's a little weird. But the torque here is a vector quantity, and it's pointing out toward me. So the way you draw an arrow that points out of the screen is like an arrow point. So this means out of, in this case, the screen or the page. That's the symbol. And if it was into the page, let's go over here. So this symbol means out. This symbol means in. And what this is supposed to be reminiscent of is the way an arrow would look. If it's pointing at you, you just see the tip of the arrow. So that's what this is. You just see the very tip of the point. If it's pointing away from you into the screen here, you see the fletching, the feathers on the back, which make an X. Okay, so that's the way this is supposed to work. So this means into the page or screen or board, and this means out of the screen or board. Okay, so in this case, how do I know that the torque points out toward me? that corresponds to a counterclockwise rotation. This force exerted on the door is going to cause the door to rotate counterclockwise relative to the axis of rotation. And the way I know that is I use what's called a right-hand rule. And let's see, let's do it this way. There's a couple ways to do this, but you point, so here you're crossing two vectors, R and F. So R comes first. You point your hand and the fingers in the direction of R so that the force vector would come out of your palm and point in the direction of the force. And then when I do that with here, you know, R goes up this way and my palm points up toward the top of my screen. My thumb is pointing out toward me. Okay, so the thumb tells me the direction of the torque. If the force was reversed, my palm would still, my fingers would still point in the same direction, but my palm would be rotated, so my thumb would point into the screen, if that was different. Okay. So the torque has a vector nature, but it also it has a magnitude, and the magnitude is a function of how big R is, but also the sign of this angle between the two vectors. And sometimes the product of these two things is called the lever arm. So R sine theta is, maybe we can call it R perpendicular to the force vector. So my picture up here, you know, if this is, let me erase these other force vectors. So we just have this one force vector. There's a component of this R vector which is perpendicular, to the force vector. It would come out like that. And the magnitude, the length of this vector of R that's perpendicular is equal to R sine theta. You think about this, let's see, theta's here, so this angle right here is also theta. So R sine theta is the length of that side of this triangle. Okay, so this is called a lever arm. All right, and you think about this, you know, if theta is equal to 90 degrees, that would be the case where F and R are perfectly perpendicular to one another. Then that maximizes, you know, sine of theta is 1. And if theta is equal to 0 degrees, the lever arm is also 0. The sine of 0 is 0. Okay, so you know, what would the situation which would give you theta equal to 0 would be you trying to close a door by pushing on its end. If I like went over there and tried to close this door by pushing on the end, it's not going to go anywhere. I've got to apply a force that makes some non-zero angle relative to the door in order to get it to rotate. All right, so just sum this up one more time. Torque is this cross product between two vectors, R and F. And the R is where the force is applied relative to the axis of rotation, but this other factor, the cross product, takes into account the angle between the two vectors, R and F. So you have the maximum effect when those two vectors are perpendicular to one another, and the minimum effect when they are parallel or anti-parallel to one another. You get no torque that way. All right, and then just to complete this, we saw last time that torque is like the Newton's second law for rotation. Instead of F equals ma, you have torque, which is like the equals I times alpha. So instead of F, force equals mass times acceleration, and you have torque equals rotational inertia times angular acceleration. Right? So this is like Newton's second law for rotation. By the way, just like Newton's second law, you talk about the net force, the total force equals mass times the acceleration. The same is true for this. If you want to know the rate of angular acceleration, what matters is not any individual torque, but the sum of all the torques acting on the system. The net torque equals rotational inertia times alpha. Okay, that's it for today. I don't see any questions in the comments. So I'll see you tomorrow afternoon to talk about the last lab of the semester. And then we'll pick it up with doing some more problems on Wednesday. All right.